Hello and welcome to this video about IP and specifically IPv4. It's been some time since I posted a video about computer networks in this channel, and as I'd like to post more frequently in the upcoming weeks and months, I've decided to change the format a bit. So you'll see longer videos with a slideshow and not just whiteboarding animations, and you'll see a lot of great content, I hope. Let me know what you think in the comments, and let's get to it. IPv4. As a reminder, IPv4, the Internet Protocol version 4, is part of the network layer as part of our 5-layer model that we've discussed in previous videos. Now, to remind you all, we have two main goals for the network layer. The first and foremost is that it's responsible for transmitting packets, these are datagrams in the third network layer, between two remote hosts. What does that mean? So the second layer, for example, Ethernet that we covered in depth in a previous video, covers transmission of data between two hosts that are directly connected, for example, via an Ethernet cable. In other words, that are one hop away from one another. The network layer allows you to go farther than that and span across multiple hops. To do that, it needs to be able to route packets, and routing is choosing the path that packets traverse through, especially when there are multiple choices for that. Let's look at this very simplistic diagram. We have two computers here, one in Italy and one in Canada. And in the middle, we have these devices called routers, third layer devices. Now, which layer is in charge here? So let's say we go from computer A in Italy, and the first thing we do is go to this router here. Who is in charge? Well, for this hop, the second layer is in charge. What about from this router to the next one here? Again, it's the second layer. And from this router to that router, it's the second layer. Notice that each one of these, when we look at a single hop, each one might be implemented with a different layer 2 protocol. For example, this could be Ethernet that we covered in depth in a previous video. It could also be Wi-Fi in this hop, and this hop might be Bluetooth. And this could be Ethernet again, and so on. So notice that the third layer is responsible to transmit information, transmit packets from the source host, in this case, computer A, to the destination host, computer B, in spite of the different protocols, hardwares, and perhaps size of datagrams in each hop. So the third layer is the one responsible to find that route and transmit between A and B. So it's responsible in this case to choose this blue path instead of, for example, let's look at this orange path as an alternative. So let's say it goes through here and here as before, but the orange path is a bit different. It goes from other routers all the way to computer B. So layer 2, the data link layer, the second layer, all of these are synonyms, is responsible for transmitting the information across a single hop, that is, two adjacent directly linked devices, where the third layer is responsible for choosing the path that is routing between the source and the ultimate destination. When we introduced the 5 layers model, we mentioned that the second layer has physical addresses for devices, whereas the third layer, the network layer, introduces logical addresses. Which raises the question, why would we need a network layer address if we already have a physical address? Can you try to think of that? Why do we need a network address in addition to a data link physical address? For example, why do we need an IP in addition to an Ethernet address? I encourage you to pause the video and think a bit for yourself. Okay, there are multiple answers here, but I think the most important thing to understand is what would happen if we had a world where you'd only have physical addresses. And for that, please be sure to watch the video we created about the second layer and specifically about switches. So say we have computer A here and computer B somewhere else around the world. And computer A wants to transmit information to computer B. And everything in this world is connected by switches, those boxes, second layer devices that we learned about. So this is a switch and another switch. Okay, I'm not going to draw all of them, but I think you get the idea. Now, say A is connected directly to this switch. Let's call it switch 1. So when A sends a frame, a data link frame, that is a packet in layer 3, sends it over to switch 1, the packet is received, or the frame is received by switch 1, and then switch 1 needs to decide where to send this. Now, if you recall, when we learned about switches, we said that by default, the switch just transmits the frame it gets to all of its neighbors. To avoid that, it needs to first learn this address. So unless S1, switch 1 knows the address of B and knows that it resides somewhere around this port, it will have to transmit the datagram to both of its ports. By that, if A sends a frame to say, a new device that no switch has learned, it would propagate to the entire internet without a logical address. The alternative is that S1 would know B's address, and then S2, that's here, would also have to know B's address and know that it's behind this port here. And then S3 would have to know B's address, and so on. Which means that we either get to a state where switches just propagate datagrams all across the internet or to all of their neighbors, which results in lots of congestion, obviously, or the alternative, which is probably not much better, is to have each of those switches include a table with all addresses in the world and where they belong. Now, this is completely unfeasible and it doesn't make sense. I hope you would agree. The idea of having a logical address is that the address is not just given to you by the manufacturer when your network card was manufactured. It's not just a physical ID that is essentially meaningless. If you recall, when we learned about Ethernet addresses, we said that with the exception of 2 special bits, we have the manufacturer identifier, the vendor ID like Cisco or Dell, and then we have a host ID, but it doesn't really mean anything other than that. If you look at the network interface and you look at its Ethernet address, you would know that it was manufactured by, say, Dell. Logical addresses work differently. They say, okay, if I need to get from A to B, I can do it logically, knowing where B is. So before we actually do that with computers, let's think about logical addresses in the actual world. Do you have such a notion, maybe something that we don't really use as frequently as we used to? Well, I think one of the best examples is actually having a physical address, a snail mail address, that is. So say I'm writing a letter and I want to put it on an envelope. I would write here, for example, to such and such name, and then I'd provide an address. The address could be, for example, 12 Wall Street, New York City, New York, USA, and some zip code. Now, what this actually says, if we look at it from bottom up, is some kind of a hierarchy. It tells me, okay, let's say this computer here resides in Germany. This computer A, it's in Germany. And it wants to send the packet to John Smith, who resides in the US. Then if it were a physical address, let's say I were in Germany, I would go to my post office and put this letter. And the people at this post office will not have to know Wall Street in New York City. They'll just say, okay, this needs to get to the States. To go to the States, we have, I don't know, perhaps a ship that takes letters to the States, and it gets out from, say, Hamburg. So we need to first get it to Hamburg. In other words, it's saying, let's look at the hierarchy. Where does this need to go? So first, let's say we're in Berlin. We're sending this letter to Hamburg first. And then there is some kind of ship that takes it. Let's have a ship here. So we have a ship, and this ship takes the letters and takes them all the way to the US. And this one actually sails to Florida. So it gets to Florida. Then the folks at the post office in Florida say, hey, this needs to go to New York. New York is up north. So let's take it on the next time we have a transit up north, maybe to DC and so on. And this keeps going until someone in the post office of New York gets it. Now within New York, the state, we need to say, okay, it needs to get to New York City. We get to New York City. And now we're asking ourselves, okay, where is Wall Street? Oh, it's in the south part of Manhattan. So we need to go there. And so on. So in other words, the navigation here is hierarchical. We keep getting closer to the destination since it has a hierarchical structure. We start from, in this case of the letter of the envelope, the bottom thing, that is the highest part of the hierarchy, and we keep going lower in the hierarchy. If we have that in logical addresses, so we have the equivalent, then it means this computer here will send the packet to the closest router. Router is usually marked like this, a circle with an X. And now this router needs to choose if it sends the packet to this router here or the other one. Now, how is it supposed to choose? So instead of having all addresses stored in memory, which is again infeasible for each of those routers, the router asks itself, okay, this needs to go to the States, right, to the US. Everything that goes to the States goes here, to this router here. It doesn't go to that router. This router sends, I don't know, maybe packets that are internal to Europe. So we go in this route. And then this router says, okay, I got the packet. And I need to send it to the States. So again, I have a few options. I can send it to this router here, or there are other routers that I might send it to. How do I know where to go? So again, we need to take the first hop that would take me closer to the destination, in this case to the States. And this continues, and let's say we get to this router and then this router here, and we keep going till we finally reached New York City. So now we're in New York City, and this router has to find Wall Street. So again, it asks itself, okay, do we need to go to, let's say, Upper Manhattan or Lower Manhattan, or maybe Brooklyn? Looks at the address, we're going to Wall Street. Wall Street is in Lower Manhattan, so let's go to this router, and so on. So a logical address is hierarchical, and it helps me navigate or route the packet closer to the destination. This is one of the main differences between logical and physical addresses. You would also notice that having both a physical address, and in the world of the physical world, it might be your ID, your national ID, for example, we have some advantages to having two addresses because it means we can have a one-to-many mapping. For example, let's say I have one physical address, that is my ID, but I have two or more, of course, two logical addresses. What could that be useful for? So, for example, I might have my own ID, I'm the same person, but I might want to have two different, say, logical addresses that different people address me with. One could be my home address, another could be my work address, different locations where I might be, even though I'm the same person. On the internet, this means something a bit different. For example, we can have one server, one machine, a very big server, that has a single address because it has a single network card. It's a bit extreme of an example, I know, it's just to convey the point, but let's say it has only a single network card, but it serves different websites or services. Each one could have a different logical IP address while retaining a single Ethernet address. Or on the contrary, I can have one logical address, but many physical addresses. Why would that be useful? So for example, if I am Google and they have, say, an IP address, of course Google has many, let's say one of those IP addresses, when we route a packet to Google, it might reach different servers for distribution, to not have one server get the huge amount of traffic that Google receives. We might want to have lots of physical addresses that are all behind the same logical address. So when we have both logical and physical addresses, we get this mapping of one-to-many that becomes possible. So a logical address includes two things. If a physical address we said include the vendor ID and the host ID, a logical address includes a network ID and a host ID. Now, a network ID is something that could be overlapping. For example, when we talked about John Smith, then he lives in the network of New York, which is also in the network of the US. So we can look at it that we have one host, say John Smith, or a specific server or computer or another network host. And this host belongs to multiple networks, belongs to the network of New York City, which belongs to the network of New York, the state, which belongs to the network of the US, and so on. So logical addresses usually include a single network in the hierarchy, but as we'll see in IPv4, actually an address means all of these things. It's a hierarchy. We'll see that in a bit. What is the service that this layer provides to the upper service? So if you recall, when we learned about the 5 layers model, we said that each layer provides a service to its upper layer. So the data link layer, the second layer, provides to the third layer the service of transmitting a datagram, that is a frame, between two hosts that are directly linked, that is linked via a single hop. The network layer provides a service for the upper layer, the transportation layer, to transfer a packet, a datagram, in the third layer between multiple hops. Which means, if we look at it from the perspective of the fourth layer, the transportation layer, we have machine A, we have machine B, and as far as the fourth layer is concerned, everything in between is just some kind of a magical cloud. Everything here is unknown. So here we might have lots of things. We might have routers. So we have a bunch of different routers, and within every link, we might have different protocols. So again, it could be Ethernet here, and it could be Wi-Fi here. And let's say the link between those routers are actually carrier pigeons. Yep, so we have a pigeon here that actually flies from router 4 to router 5, transmitting packets each time. And let's say there is a sniper in this link that is between, I don't know, Sweden and Denmark, and the sniper decides to shoot our poor little pigeon. And no, I'm not for hunting pigeons, it's just for the example. And now this pigeon gets hurt and can't fly anymore. Someone needs to restore that link, that is, send another carrier pigeon from router 4 to router 5. That's an issue for the second layer, the specific implementation of the carrier pigeon protocol. By the way, it is a protocol. I'll talk about it on the next video. So let's say we have that issue here, and then for the third layer, it needs to find another route. So if before the default route to get to B was the green route, like this, and so on, now the third layer decides that the route should go somewhere else, maybe the orange route. So it starts the same, but then it continued from here to, say, router 6, and so on. As far as the transportation layer, the fourth layer, is concerned, none of this exists. What it is a cloud. So if you look at it from the fourth layer's perspective, what you see is this. You have A, you have B, you have a cloud. That's it. In case the packet dropped, so we weren't able to transmit it, it depends. If the third layer is a reliable third layer implementation, it would make sure the packet still gets received by the other side. We'll talk about it in a bit. If not, it might just be dropped and the fourth layer will have to send again. But all of this, Ethernet, Wi-Fi, carrier pigeons, snipers, all of this is none of its business. And that's the beautiful thing about the 5 layers model, where each model just hides or abstracts lots of the implementation details from the upper layer. So let's talk about IP. So far we talked about the network layer in general, now to IP and specifically IPv4. So IP stands for the Internet Protocol. It sounds a bit funny today because everything is on the internet, but back in the days in 1981 when this RFC was published, we were talking about the Internet Protocol for this new network called the Internet, RFC 791. If you don't know what RFCs are, these are the documents that describe what the protocols or other things should look like. I talked about them on another video, so check that out. And according to the original RFC, each network interface in the world should have a unique address on its own. It's not like that today. We'll solve it gradually. We'll start solving it today. We'll continue when we talk about the fourth layer. But for now, we just need to know that in theory, each network interface should have a unique address. And an IPv4 address is 4 bytes long, usually written as 4 decimal notated numbers delimited by dots. For example, 1, 2, 3, 4. That's a valid IP address. Also 23, 41, 55, 91. This is also a valid IP address. What about this one? 23, 41, 278, 91. So no, this one is invalid because 278 is not a decimal number that can fit into a single byte. A single byte can have the numbers of 0 to 255 in decimal notation. As I mentioned before, network addresses have a network ID as well as the host ID. So there are a few different ways to do it. The most common one to do it nowadays is called subnet masks. The idea is this: when you convey a network address, such as 192.168.0.1, it's not enough to add just that. You also add a subnet mask. That is the number of bits that are used to denote the network ID. So in this case, the 16 most significant bits are the network ID, which means the 16 least significant bits are the host ID. So if we'll take this address, 192.168.0.1, and we only look at the most significant 16 bits, we get 192.168, and whatever follows is within that network. There are different ways to notate a subnet mask. One is with this slash number of bits notation. The other is to have a mask written like this in decimal form, where all the bits that are on are the significant bits that are part of the network ID. So if I take 255 and I convert it to binary, I get 8 times 1, and then another 1, and now 0, 0. So this is just 255, 25500 in binary form. And of course, I didn't write here 8 zeros each time just to be brief. If we look at these are 16 ones, which is just the same as writing /16. So these are two different, very common ways to denote a subnet mask. So now every address that starts with 192.168, say 324, resides within the same network as this address here. So this /16 subnet mask means that this is the network ID, which means this host ID is 01. This is host 0.1 within the network 192.168. Let's see another example. So now we have 192.168.0.1/8. In other words, only the first 8 bits are the network ID, so only 192. So whenever an address starts with 192, it's within the same network. Note that this means that, for example, this address is within the same network as 192.168.0.1 with a /8 subnet mask, but it's not the same address as with the /16. Note that the subnet masks don't have to be multiples of 8. You could have a subnet mask of /9, 10, 11, but it's more convenient to have multiplies of 8 because it's easier here, as you can see, so we'll exercise other subnet masks later. There are a few special IP addresses in addition to the normal IP addresses and the subnet masks. One such address is the broadcast address 255.255.255.255, which theoretically means all machines on the network. So on the internet, it would be all machines on the internet. You can't really send a packet to all machines on the internet for various reasons. Most notably, it would create lots of congestion and denial of service. But theoretically, it means all hosts on the network, on the internet. Usually, it means all hosts within the local network. If you recall, when we learned about Ethernet, we had the broadcast address of FF 6 times. Both of these, when you convert them to binary, are just all bits set to 1. So when all bits are set to 1, this is the broadcast address. Again, this means all hosts within the network. Another special address is 0000, which notes this host. So this seems a bit weird. I mean, why would you want to write this host? So there are two main reasons to use this address. One is when you don't yet have an IP address. So before having an IP address, and you want to get an IP address, as in contrast to, say, Ethernet addresses, you don't get them from the factory. It's not part of the network card. It's something you get dynamically. So if you don't have an IP address, but you want to communicate over the IP protocol, for example, with DHCP that we'll cover later, you will have to send with the source address of 0000, meaning this host. In other words, I don't have an IP yet. Another option is when you use sockets and you want to listen on any incoming communication. So when you use a socket and you want to listen on all network interfaces, when you use sockets, for example, with Python, you can use the socket.listen and you can provide a tuple of the IP address you're listening on and also the specific port. If you have multiple network interfaces, for example, one Ethernet and one Wi-Fi, or just two Ethernet network interfaces, you might say, I'm listening to any incoming connection for a specific port on this machine, and for that you'll say I'm listening on 0000. The third special IP address is 127, and everything after that. Usually what we use is 127.0.0.1, but that's only by convention. You could use any other. According to the RFC, everything that starts with 127 is within this loopback. What is loopback? Loopback basically means that packets that you send to this IP address never leave your network interface onto the actual network. So you can think of it as a virtual networking interface that resides within your operating system. Why is that useful? So mostly for debugging. Let's say I were to implement a chat application, a simple chat application. So I have machine A and machine B. So here is machine A and here's machine B. And each of them run a simple script that listens to packets and shows the user what the other person has written and so forth. So I get a bidirectional link here. Right, now let's say I want to debug it. So I would have to sit physically by, say, computer A, write something, press enter, walk to computer B, see if the message was received. If not, I would have to debug why doesn't it appear on the screen, and so on. What might make more sense is actually to have two processes on the same machine. So consider process A and process B within my own computer. So I have my own computer And I have two different processes. And we communicate by the fact that instead of writing an actual IP address, one that could be used by a network interface, a physical network interface, we send a message from A to B, which both have, for example, the IP address of 127.0.1, but they have different ports. For example, this one has the port 1337, and B is 127.0.1, 1338. The application layer and the transportation layer are oblivious to this. They don't know that you're using a special IP address for a loopback. Every communication, all of the implementation is the same regardless of that, so that when you're ready to finish debugging, you can just switch the IP address from 127.0.1 to the real IP address used by the network interface, and everything will work as is. So mostly for communication between processes on the same machine, for example, for debugging, we use loopback. One more thing that is very rarely used is the ability to send a remote broadcast. So for example, let's say we have the network 123.0/24. That is everything that starts with 1 to 3 within that network. And let's say I'm not part of this network. If I'm part of this network and I send a packet to this broadcast address, it basically means all of those hosts on 1 to 3. But I could be outside that network and send a packet to 1, 2, 3, 255. This basically means all hosts within the 1, 2, 3 network. Given the snail mail example, I could send a letter to all citizens of New York. So I'm looking at the network of New York City, and I'm sending all of their citizens, all of the people who live in New York City are the recipients of my letter. Other special addresses are called private addresses. And this is something we have to start talking about when we talk about IP, but we can't really finish discussing it here before we keep on and talk about upper layers, specifically the transportation layer, and we'll address it in another video. But to start with, so why do we need private addresses and what are they? In the beginning of the 1990s, something amazing yet horrible happened. That is, there was an actual outage of IPv4 addresses. That is, a baby who was born in the 1990s or later in the early 2000s or even today. A baby is born and doesn't get their own IP address. You don't seem horrified enough. Let me be clear. A baby is born and they don't get their own IP address. And you know why? Because there are not enough to give. For various reasons, and some of it relate to the fact that IANA, this organization that is responsible for assigning addresses, wasn't being super responsible when it addressed addresses in the beginning, but also no one anticipated that this network called the internet, originally meant for communication between research departments, would be such a huge success. So we basically had no IP addresses, and then what are we going to do? I mean, IP is supposed to provide each network card with its own unique address, and this is how you communicate over the internet. So what do? Well, the basic solution to this is to have two separate kinds of addresses. Without private addresses, what you get is this. Let's say we have a network, a home network at home. Let's say I have this network. So this is my network. Here I have a router. And my router has two different ports. One for the outer world, let's call it outer, and the other for the inner world, for the inner network. These are two separate network interfaces, two separate Ethernet addresses, hence two separate IP addresses. And here we also have a switch, the second layer device. The switch doesn't have an IP address, it's a second layer device. It doesn't need IP addresses. In parentheses, we're always talking here as if we were living in the topic model of the 5 layers. Real switches usually have IP addresses because you would want to configure them remotely, but I'm putting that aside for now. Okay, so we have a switch without an IP address, and then we have a few machines at home. We have A, we have B, and we have C. How many IP addresses would this very small network take out of the world? So by default, it would take one IP address for the outer port of the router, a second one for the inner one, and one for each computer. That is 5 addresses. If I had a larger network with, say, 20 computers, I would get at least 22 IP addresses. Now, having private addresses means that I only have to use one IP address that is taken from the global pool of IP addresses, and all of the rest are private addresses that cannot be routable on the internet. So only the outer port of our router will get an actual IP address. Let's say it gets the IP address 1234, lucky me. So let's say I have this IP address and I need to pay for it, and it's a real valid global IP address, and the other hosts here all get private addresses. For example, the address 192.168.0.1. This is a private address. It means that I can have this address on my network, you can have it on your network, almost every network in the world can have this address. It's reusable, it's private, and it cannot be routed. Why can't it be routed? Because if this network lives, say, in Italy, and we have another network, say, in France, let's have the green network in France, and the router here sends a packet to another router on the internet, sends a packet with the destination of 192.168.0.1, this router can't know what to do. I mean, is it the 192.168.0.1 in this network in Germany? Is it in another network in France? Is it in a network in the US? Since these addresses are shared, you cannot route them, so routers just drop these packets altogether. So we haven't yet solved the problem of the outage of IP addresses, because now we have private addresses, but it's unclear how I can communicate it between devices that have only private addresses. So we will answer that in a future video. But for now, I want you to know that there are 3 different ranges of IP addresses that are assigned specifically for private addresses. First one is 10.0.0.0/8. In other words, any address starting with 10. The other is a bit confusing because it's using S/12 subnet mask, so 172.16, and in a moment we'll exercise what that actually means. And the third one is 192.168.0.0/16. That is everything that starts with 192.168. So when we talk about 10.0.0.0/8, how many options for hosts do we have here? So 4 bytes mean we have 32 bits, right? If we take 8 bits for the network ID, it leaves 3 different bytes or 24 bits for the host ID. So we are talking 2 to the 24th power of options here, which is 16,777,216 different options, which is a lot. If we talk about 192.168/16, so here we have 2 bytes, 16 bits that are reserved for the network ID, and we have 2 bytes, 16 bits for the host ID, 2 to the 16th power, 2 to the 16th power, so we have 65,536. And last but not least, we have the 172.16/12. Now, /12 means that if you take 32, subtract 12 from it, we get 20 bits. So 2 to the 20th power is 1,048,576 options. Which addresses actually reside here? What do we do with that /12 notation? So let's think about it. The first 8 bits are clear, right? We have 172. And then when we talk about 16, let's convert this to binary. So 16 in decimal notation is in binary. So we have this is 1. Let's practice binary for a bit. So the first bit, if it's on, it's 1. This one is 2. This one is 2. This one is 4. This one is 8. And this one is 16. So basically, what this means is that every address that starts with 172, that's the first 8 bits, and then 4 bits of 0001 will reside in the same network. So this range we get is between 172.16, that is with 0001 here and 0000 for the remaining bits, all the way till these are all ones, which means we add 8, 4, 2, and 1 plus 16. So we get altogether 31. So any address that starts with 172.16 till 31, so that includes 172.17, 172.18, and so on, will reside within the same network. Any address you see within those networks are private addresses. They cannot be routed on the internet, and again, we still need to address how you work with them, pun intended, with the word address there. That is the initial bytes that precede the actual payload, if exists, of the packet itself. What I want you to gain by this is to know every bit and byte in the IPv4 header, and we'll do it gradually. So not everything will be covered on this slide, but we will cover it all in this video. Right, so just to get acquainted with these kind of diagrams, because it's the first actual one we've seen, you can see here that you have some marks regarding the bits. So this is bit 0 all the way to 31. So we have 32 bits, that is 4 bytes on each line. You can also see that the minimum length of the IPv4 header is 20 bytes. So here, that's in case you don't have options. I would say that options are not very frequent on IPv4 specifically. So usually we see packets with only 20 bytes of header. Let's go through the header fields one by one. We'll start with the version. And my dog decided to join because this is an exciting topic. Welcome, Hook. All right. So the first field we see here is the version field. Why do we start with the version? And I'm going to ask many questions here. Pause for a second and answer myself, but if you want, I encourage you to pause the video and try to answer for yourselves. So why do we start with the version field? Why is this the very first field? Well, the answer is that the rest of the header depends on that version. That is, in this case, it will be version 4. So if we look at it in binary form, it would be, can you do it? It's 4 bits long. What would it be in binary? So it'd be 0100, which is in decimal form 4. So version 4 for IPv4. If it were, say, 6 for IPv6, then the rest of this header looks different. So first comes the version. Then we have another 4 bits, also called nibble, by the way, that says IAGL. IAGL stands for Internet Header Length. Why Internet? Because IP is the Internet Protocol. So it's basically the IP header length. Why do we need to specify the length? Well, because there might be options. If you have options, then the header is longer than 20 bytes. So we have to specify that. By default, it would be 20, but the creators of IP did something quite smart here. They decided to not write 20 because that takes too many bits, but write the number of words. So basically what you do is you write the number of the words. So basically what you do is you take the number here and multiply it by 4. So to get 20, you write 5. So if we go back to binary, this would be 101, which is 5 in decimal notation. So when you look at Wireshark, and we'll do that very soon, you'll see that almost every IP packet starts with the byte 45, which means version 4, and 20 bytes of header. Again, you take the 5 here and multiply it by 4. If you have a 24-byte long header, it will say 6 here. Right, so we start with 4, 5, and then we have type of service, or TOS for short. Type of service theoretically allows you to denote the, well, type of payload of what this packet is actually conveying. For example, let's say you have voice over IP versus, I don't know, a very large image that you're trying to download. Then if you denote that the first one must be received very, very fast because I'm on an online voice over IP call, then it might be prioritized over other packets on different routers. The reality is that outside the local network on the internet, it's very hard to actually rely on that because everyone could just say, I have the most urgent, most important service. So usually what you see here is just a bunch of zeros. Then we have a total length. Total, that is the header length plus the payload length. Why do we even need a total length field? I mean, you're supposed to know the length of the payload given what the second layer has provided you with. And you know the header length from here, so why do we need a total length? So it could be a payload length rather than a total length, but the sad truth is that due to some issues with some second layer protocols, Ethernet, if you remember from that video, the second layer doesn't really ensure that it provides you only with data. It might also provide you with some padding. That's why we need the total length to differentiate the actual payload, the actual data being conveyed over this packet from the padding. If you are curious about that and what happened in Ethernet, check out that video we created. All right, you'll also notice that the total length here, it is a field with 16 bits. So from bit 16 to 31 inclusive, we have 16 bits, which means that the maximum length of an IPv4 packet is 2 to the 16th power minus 1, of course. So we have 65,535 bytes. That's the total maximum length of an IP packet in IPv4. The next row is all about fragmentation. And fragmentation is a fascinating topic that I would denote a different slide or a couple of slides to later. So we'll get back to that. I'm skipping it just for now. Next, we have the time to live, or TTL field. It's a bit confusing by its name because it doesn't have anything to do with time or living, I guess. But let's think about this scenario. So let's say I have computer A that wants to send a packet to computer B, and there are a few routers in between. Let's just use another color for that, and I'll write here R1. Say router 1, and then we'll go to R2. And actually, I won't use arrows now. Explain why in a sec. R3, then we have R4, then we have R5, then we have B. And R4 is also connected to R2. So let's say A sends a packet to B. So this is the packet. And A wants to send it to B. So I sent it to R1. R1 looks at the destination address, says, oh, B, I need to forward it to router 2. So R1 decides to forward this packet to R2. So now the packet is here. Now R2 looks at this packet and says, oh, B, I need to forward it to R3. Sends it to R3. Then R3 says, oh, I need to route it to B, so I need to forward it to R4. Then R4 says, okay, I want this packet to reach B, so I'll forward it to R2. That's a routing mistake, of course, but it happens. And then we go from R3 to R4 to R2, and then R2 says, hey, a packet for B. Who do I forward it to? R3, which then forwards it to R4, which then forwards it to R2, and so on. And this loop is problematic for various reasons. The obvious one is that this packet will never reach B. That's a problem we should address. But the worst problem, perhaps, is that it creates an ongoing and potentially infinite congestion on the network, because these routers will have to go through processing this packet over and over and over again. So to avoid these infinite loops, the creators of IP added the field TTL. Let's see how it works. So let's say A starts and puts a TTL of 8 on this packet. So when it reaches R1, R1 decreases the TTL to 7. Then it sends it forward. Forward it to R2, which says, okay, TTL is now 6. Forward it to R3, decreases it to 5. R3 decreases to R4. So this is 4. And if everything were okay, R4 would transmit it to R5. That would reduce it to 3. And then to B, that would reduce it to 2, but it's already the destination. On this case, though, R4 says, okay, I reduced the TTL to 4. I'm now forwarding to R2, which reduces it to 3. R3 then reduces to 2. Then R4 receives the packet and reduces it to 1. Then to R2, which reduces it to 0. And when we reach 0, R2 doesn't forward it anymore, but drops the packet and possibly also sends another kind of packet we'll learn about later to A saying TTL expired. So the goal of TTL is to limit the number of hops. So that's basically a hop limit, the number of hops a packet could go through before being dropped. So the name time to live might be a bit misleading, but that's what it is, and that's what we use, at least on IPv4. By the way, on IPv6, it was changed to hop count, which I think more accurately represents its actual meaning, but many people are just used to saying time to live, which makes more sense in the world of caches. So when you have an entry and it lives in the cache for 20 seconds, for example, never mind. All right, so that was time to live. And time to live, what is the length of this field? It's correct, 8 bits. So 8 bits, it means it's between 0 and 255. So the maximum number of hops that an IPv4 could transfer through is 255, which is way, way, way more than enough. You would know that different operating systems usually have different default values here. Most Windows versions start with a time to live, a TTL of 128. Most Linux distributions start with 64, and both are way over what you need for a packet to get from one side to another over the internet. The next field is the protocol field. The protocol field denotes what the payload is. So what's this IP packet is carrying. For example, if you write here 1, it means the payload is ICMP, which we'll learn about later. It could also be TCP or UDP, and each one has a different corresponding value. This is important since when you look at the packet, so let's say you see it as an envelope, and you say, okay, this envelope has all the metadata, right? It's what you have in the header. So you know it's destined to me from the destination address that we'll get to in a sec. And then you say the protocol number is, say, 6. So this is TCP. So what the IP layer, the network layer in this case does, is open this envelope, take the payload that resides within. So let's say this is the payload, the fourth layer, the TCP, and it knows this is TCP, so it can provide it to the TCP handler, the code that deals with TCP. If it were, say, 11 in hex, then it would forward it not to the TCP handler, but the UDP handler. So this is, in a way, telling you which layer, which implementation, which protocol is the upper layer, and then who is supposed to consume this packet. Next, we have the header checksum. If you recall from previous videos, a checksum is a way to verify that the information, possibly the payload, in this case, only the header, is valid. So IP is not a reliable protocol. It's not a reliable implementation of the network layer. Not at all. It's a best effort kind of service. That is, you send a packet, you hope it will be received, and you hope it will be received correctly. If a sender really wants to ensure the correctness of the payload, they should use a reliable implementation of the fourth layer, for example, TCP. In parentheses, I would say this is not exactly accurate, but I will get back to it after we learn about the fourth layer or when we get to IPv6, and we'll discuss why actually we don't really have to have a checksum in the IP layer for you to know that the payload you received is valid. We'll talk about it another time, but just so you know, basically every second layer implementation on the internet, Ethernet inclusive, already has a checksum so that the payload is guaranteed to be valid based on that. Why do we use a checksum for the header? Well, if you changed, for example, the destination address by mistake, so one of the bits here, let's say it was 1100101010 and so on, and something here changed, and instead of this 1, you get a 0 by mistake due to an error, which could happen, of course. If you don't know that, you might just route the packet to a completely different destination. So we don't want that. That's why you have a checksum, but on the header only. Then we have 4 bytes for the source address. Say we send the packet from 2222 to a destination address, which is again 4 bytes, say 5678. And that's enough to have a valid IPv4 header. Now, you might also add options. Options here are not as interesting because they are not as frequently used, just so you know what some might be. So we have here loose source routing, which means you provide in the options a bunch of intermediate addresses you want the packet to be routed through. So you're saying, okay, I'm sending a packet from the States to, say, Germany, but I want it to be forwarded, routed on the path somewhere through this specific location in, say, London. This is loose source routing. It means I want it to be routed there, but it doesn't have to. Don't drop this packet if you can't provide it through London. Strict source routing, on the other hand, which is another option, says you have to go through these destinations if you can't just drop the packet. So these are just examples of options. Again, not too interesting to know in IPv4. And we here also have padding. Why do we need padding? So the answer is right in front of you on the slide. So again, I encourage you to think for yourself. All right, so we said that the IAGL field is in multiplies of 4. So I can write here 5, and then if I want to add an option, if it's 4 bytes or less, then it has to be 6, which denotes 24 bytes. So I can't possibly provide here a length that is not in multiplies of 4. I can say the length of this IPv4 header is 22 bytes. I can't do that. I can say this header is 20 bytes long, 24 bytes long, 28 bytes long, and so on. Which means if an option is, say, 3 bytes, I would have to pad the remaining 1 byte with zeros. Okay, so by now we understand the IPv4 header with the exception of this line here regarding fragmentation that we'll get to later. Let's move on. So since we've shifted to this new format where the videos are longer, I figured it would make sense to have some breaks during the video where I ask questions and you make sure you understood what I was trying to convey. If not, I hope these questions and answers will help you. And if something is still unclear, as usual, please post your questions in the comment section below and I'll be glad to answer. All right, so are 185.24.5.18 and 185.23.5.10 on the same network? What do you think? Well, first of all, it depends on the subnet mask. That's right. For example, if the subnet mask were /8, would these be on the same network? The answer is yes, because they share the same most significant 8 bits. 185 here, 185 here. What if it were, say, /16? Would it reside on the same network? So the answer is no, because with /16, here the most significant 16 bits are 185.24, and here they're 185.23. So we have different most significant 16 bits. All right, but what is exactly the threshold between them? How many bits? So we know it's more than 8 or at least 8, and less or exactly 16. But is there a more granular threshold we can find? So to find that, the easiest way, I believe, is to convert to binary. So let's convert 24. If you're not comfortable with converting decimal to binary, there are other videos about that. I'm not going to focus on it in this video. You can also use the built-in calculator that comes with your operating system. In this specific case, let's do this. Let's take 24 and convert it to binary. So 24 is 16 plus 8. So I'm going to do 16, 8, and then I'm going to pad this with 3 additional zeros. So what you get here is, again, this is the 1, 2, 4, 8, 16, and so on. 8 plus 16 is 24. Good. Now let's look at 23. Let's pick another color, blue. All right. So 23. If we convert that to binary, this would be not 16 plus 8, but 16 plus 7. So we get 16 plus 7, 23. So how many bits are the same here? So if we go from the left, we're looking at the most significant bits again. So we are looking at 0, 0, 0, 1, and that's it. This bit here is 0 when it's 23 and 1 when it's 24, which means it's different. This means that if we use a subnet mask of 8 bits plus these 4 bits, we get to /12. These are still in the same network, but if we change it and we look at a subnet mask of 13 bits or more, they reside on different networks. This is an example of having a potential subnet mask of not a multiply of 8, but something in between. I think it's good to exercise it to feel comfortable with these kind of subnet masks and in general converting binary to decimal. Let's move on to the next question. So what's the RFC number for IPv4? The RFC number is 791, and as usual, if you have more that you'd like to know about this protocol, you're welcome to open the RFC. Just type in RFC 719 on Google or ChatGPT or whatever you're using nowadays, and you'll see more information. What's the broadcast address in IPv4? That's right, it's 4 times 255. So 255, 255, 255, 255, which, as we said, resembles the broadcast address of Ethernet of all FFFF. That is, all bits are on for the broadcast address. The broadcast address denotes all the hosts on the network. Why do we need private addresses? So, as we said, there was a real, not theoretic, real outage of IPv4 addresses from the beginning of the 1990s, so a long time ago actually. And again, a baby was born in the 1990s or later and couldn't receive their own IPv4 address. And that's a real problem, because if you don't have enough IPv4 addresses for people, you obviously don't have enough IPv4 addresses for all of their devices. Because I don't know about you, but I have at least 2 computers and 1 phone and a few other smart devices that have their own IP addresses. So how does that work exactly? So we said we couldn't yet solve this issue in this video. We'll need some more knowledge that we'll acquire on subsequent videos. But so far we said that you could assign some of the addresses, private addresses that are non-routable, that could be reused over the internet, and only have one external global address for your network. For example, your router would have one real IPv4 address, a routable one, and all of the devices behind this router, like your computer, like your sibling's computer or your spouse's computer, and your, I don't know, printer or smart TV and so on, they will all have private IP addresses, and we'll get back to the issue of IPv4 outages and how it was solved later. I would say that the real solution is IPv6, which thankfully has become way more popular regarding internet traffic in recent years, but still IPv4 is very much out there, and you could wonder why for so many years we've known that it's an issue yet. And the RFC for IPv6 was published in the 1990s. How come we still have IPv4? Well, we'll answer that on another day. Let's keep going for now. So can you name IP fields that we've just learned on the previous slide? We have the version, which has to be first, so you know the rest of the header. Then we have the IHL, Internet Header Length, multiplies of 4, denotes the length of the header. Then we have a type of service, which could say this packet is a voice over IP. This packet is just some management data between routers. This one is for downloading large files. And routers could potentially treat those packets differently. For example, prioritize transmission of live packets over others. We also saw the total length field, so how many bytes this packet, header, and payload included sum up to. We skipped all the fields regarding fragmentation. We'll get back to them soon. Then we discussed also, do you remember? Time to leave, TTL, which basically means the number of hops that a packet could reach. We had the protocol, the next layer, what the payload is. We then had the header checksum. So a checksum of the header only to make sure that every one that was sent is a 1 received and every 0 sent is a 0 received. On the other end, we then have the source address and the destination address, 4 bytes each. What byte will a typical IP packet begin with? 4, 5. Why is that? The 4 means that this is an IPv4 packet because it's the version field, and then 5 in the IAGL field means this packet has a header which is 20 bytes long because we have multiplies of 4 there, so 5 times 4 is 20. Moving on. So now we're looking at a very simple network. I didn't even include a switch here. We're looking at a network where you have 5 computers denoted C0 for computer 0, computer 1, and so on through computer 4, all of which are connected via a single cable. We don't really have these networks nowadays. It's just for simplicity's sake. All of them are also in the same segment and also in the same collision domain. If you remember what that is from when we discussed the second layer, means that when we send the frame, say from C0 here, all of the other machines will receive it. So let's say C0 now wants to send a packet and it wants it to send it to C1 specifically. And let's say C0 somehow even knows the IP address of C1. So let's say C0 wants to send a ping to C1. If you're unfamiliar with ping, it's a very simple utility. You say ping, then the name, it could be a domain name or an IP address of another entity. And if it receives your ping request, it sends back a response, also called a pong, or a reply. All right, so C0 wants to send a ping to C1, and C0 even knows the IP of C1, but as you probably recall, this IP packet is actually a layer within a bigger envelope, which is, in this case, say, Ethernet, the second layer. So what we have here, we have the IP layer, and all of this is actually the payload that would be inserted. So now I'm gonna put this inside a bigger envelope, which includes the Ethernet fields. And now we need to fill in some of the fields that are going to be sent. So the source IP is clear. We know our source IP. How does a machine know its own IP? That's another question that we'll answer shortly. Let's say we also have the destination IP in this case. We know the IP of C1. We also know our source MAC, the Ethernet address, the second layer address. How do we know it? I've received the source MAC from my manufacturer. I mean, it's literally burned on my NIC, the network interface card. It's on the hardware, so I know what it is. But what about the destination MAC? I mean, I'm supposed to put it, or the network interface card is supposed to include it in the outgoing frame, in the Ethernet layer. So to find out the destination MAC, the destination, say, Ethernet address, we have a protocol just for that, for translating between a network layer address and a data link layer address. Now, this is a glue. It glues a gap between the two layers. I know when we introduced the 5 layers model, we talked about it as everything is amazing and every layer just knows what it has to know and it doesn't have to care about the underlying layer. It's good in theory. In practice, there are still some gaps where we need, say, glue. So the protocol I'm going to introduce now is this sort of glue. The example we're showing here is to translate from IPv4 address, that is the destination IP of C1 in this example, to its corresponding MAC Ethernet address. Note that this same protocol can be used to translate any network layer address into any data link layer address. So, what does it look like? At first, C0 needs to resolve the IP address of C1. So now C0 sends a broadcast message to everyone in its segment saying, "Hi, I need the physical address of the device with IP1, that is the IP of C1. All of the other hosts on the network, on the segment, receive this message. What they're supposed to do at this point is to look at it, say, okay, he's asking about an address. Do I know this address? Does it belong to me? And now it really depends on implementation, but at least the machine whose address is the one being queried would respond. So in this example, C1 says, hey, I'm the device you're looking for, and this is my address. By default, this response is sent as unicast only to C0, even though on this specific network architecture, it doesn't mean too much in terms of where the frame actually leads, but the network interfaces of the other machines might say, oh, this is not for us, its destination address is unicast and for someone else, and then discard it silently. On some implementations, if C2, for example, knows the corresponding MAC address for this IP address, C2 can also reply. It depends on implementation and out of scope for now. The protocol to do that is called ARP or ARP, Address Resolution Protocol. It was defined in RFC 826, and there are some useful commands that help us see what the ARP cache actually looks like. And by cache, what do I mean? So let's say that C0 queried for the IP of C1 and got the corresponding MAC address. Now, C0 could keep asking every time it needs to communicate with the IP of C1. So say they were corresponding on, say, instant messaging, C0 could send an ARP for every message. Now, this is a lot of overhead, and I hope you remember this term from previous videos. Now, instead of paying that overhead of asking for the MAC address that corresponds with the IP address every single time, C0 can actually store this mapping between the IP of C1 and the corresponding MAC address in its cache. So it's a table mapping from IP to MAC. If we want to see this table, we can use ARP-A, and I'll show it in a sec. Say that in general, there are two types of records in this table. There could be dynamic records that are inserted into this table when you use ARP. So when you send a request and receive a reply. There could be other entries, static entries, that are inserted either by the operating system. For example, it could specify that 255, 255, 255, 255 corresponds to FFFFFF and so on the Ethernet layer. It could also be inserted by you or by an IT person. And as I mentioned in many videos in the past, we love the IT people. Now, in order to save them time from configuring this statically for every machine on the network, which, well, theoretically, we could have done, ARP makes this much easier by resolving dynamically. So let's see what the outputs of these commands look like. So I'm using ARP-A. And as you can see, I have two separate interfaces here, each one with a corresponding IP address, one starting with 192.168. It's, not surprisingly, a private address, and also 172.28 is a private address from another subnet. And as you can see, we have here a few IP addresses that correspond to MAC addresses that are set dynamically. As you can see, type dynamic. So this is probably, just by looking here and knowing that it's in my ARP table. Do you have a guess what this is, what this device is? So I assume it's probably my router, right? It's the device that gets all of the traffic that I send outside my segment, or everything I get from outside into the network. So it just makes sense that at some point I queried the IP address and got back its Ethernet address and that I want to store it. In addition, we have some static mappings. This is the broadcast address we mentioned. And here you can see other addresses, namely multicast addresses. So if you recall, when we learned about Ethernet, we said that there is unicast frames sent to a single device on the network. There are multicast. Multicast are sent to multiple devices. Broadcast is a specific case of multicast. It just says all of the devices on the network. But you could also have, say, all the routers on the network or all the printers on the network. So these are different multicast addresses. And here we can see the addresses on the other network interface. The same command can be used on OS X or Linux. Now, if you want to use ARP-S, we can use ARP. We can see here that we can use ARP-S internet address, that is the IP address, and then Ethernet address. So to do that, I could use ARP-S, and you can actually see an example here, ARP-S, and this is an IPv4 address, and this is a corresponding MAC address that would add this as a static entry onto the table. Okay, so now we understand how to map from IP addresses or network layer addresses in general to MAC addresses. All right, so I started sniffing with Wireshark, and I put the ARP filter, and I don't see any frames at all, which kind of makes sense. I mean, all of the ARP entries are probably in cache, at least everything I need. So let's empty the cache. Okay, so I open the command line as administrator this time because I want to delete entries from my ARP cache. So to do that, I can write ARP-D. And since I just want to delete everything, I'll use ARP-D star to delete everything. Okay, and now, as you saw, instantaneously, we can see an ARP request probably to the router. So here we see, let's see what it looked like. So on the second layer here, we have Ethernet. The destination is broadcast. As we said, all of the devices on my network will receive this frame and might respond. The source is my MAC address. The type is ARP. If you remember, on Ethernet, we have type field, at least in Ethernet 2, which is kind of the equivalent of a protocol in IPv4 header. This is what type of payload or upper layer this frame or packet, in the case of IPv4, is transmitting. Then we have the upper layer ARP, address resolution protocol. You can see the hardware type is Ethernet and the protocol type, that is the third layer protocol type, is IPv4. Again, it could be a mapping between different addresses, for example, IPv6 to another type of hardware. We have the size in bytes of the hardware address. So Ethernet addresses are 6 bytes long. IPv4 addresses are 4 bytes long. The opcode is a request because we're asking for something. And you'll see here we're sending, I am the one to request this. This is my MAC address. This is my IP. I'm looking for the IP address of this destination. I don't know who it is, so I leave here everything as 0. Then we can see the response. So someone responded to me in unicast. We can see that the source address in the Ethernet layer is the same as the MAC address that is resolved here. So we get an ARP reply this time. So the opcode is 2, reply, not 1, which is request. And the frame is sent directly to me. We can see that also on the Ethernet layer, that it's a unicast message sent directly back to me, the one who asked for this MAC address. It's time to combine some of the things we learned on both the third and second layer and ask how the operating system routes a packet. So, how the operating system routes a packet. Before we look at the next slide, I want to describe the situation. So let's say we have computer A who wants to send a packet to computer B. And theoretically, there are 2 scenarios here. The first scenario is that they reside within the same segment. That is, there is only one hop between A and B. For example, let's say A is connected to a switch that is then connected also to B and maybe to some other machines. And as a reminder, a switch doesn't count as a hop. Neither A nor B are aware that there is a switch here. And basically, this is the network. Optionally, there are additional devices, but it doesn't matter. If A and B are connected via one hop, then on the second layer, the next hop for the message to go from A to B is actually B. It's a direct connection. So this is scenario 1 within the segment. Scenario 2 is where we have A and B again, but A is not connected to B directly. B is somewhere on the internet. It could be 2 hops apart or 40 hops apart. We don't know, but they're not on the same segment. So we have a network for A, and A is connected, let's say, to switch, to a few other devices as well, possibly, and in the end, also a router that connects A to the outer world. And from that router, there might be, again, 40 different routers in between, or it might be direct, any number of routers here. And in the end, there is a router here that is linked directly to B. In this case, where B is outside the segment, or not within the segment, that is, B is 2 hops away from A, or more than 2 hops away, then A, in order to reach B, needs to send the packet through an intermediary, through a router. So on the case where B is within the same segment as A, the packet will travel like this, directly from A to B. Whereas on the case where A and B do not reside within the same segment, A will send the packet first to the router, and the router will route it all the way till it gets to B. If we're focusing on A, or the operating system running on A, the operating system needs to ask itself where it transmits the packet for B. Does it send it directly to B, to its corresponding MAC address, or does it send it to the router and asks the router to route it to wherever B is on the internet? So that's the main distinction. So the OS gets a packet. If the destination is within the segment, what we would do is send an ARP request to resolve the corresponding MAC address for, say, B's IP address, and then we can send the packet directly. That is, on the second layer, it would be the destination address of B directly. What happens if the destination is not in the segment? Then we would need to send it to our default gateway, which is another way of saying the router that we use to send all the packets that will then go outside of our segment. So how do we know if another machine is on our segment or not? Theoretically, there are different ways to enter this, but most of them wouldn't really work. I mean, we could send a broadcast message to B, and broadcast by default doesn't cross segment boundaries, and then see if I get a response. If I get a response, then B is within my segment. The problem with that is that B might not respond even if it is within my segment. For example, if B is just turned off for some reason, right? It's a machine that's within my segment, but it's turned off. Another option would be to have the IT person write a list and put it on every machine of what other machines are within the network. This sounds like a very hard job for the IT person, and as I said many times in the past, we love the IT person, okay? We definitely don't want the IT person to go to all machines on every change in the network and need to update all of these tables. Another option would say A considers B to be in its segment if they have the same subnet. Now, this is a bit confusing because let's say we have A here and we have B. And A is trying to understand whether B is within the same segment. Now, A's IP address is, say, 192.168.0.1. What about B? So let's say B has the address 192.168.0.2. Do they reside on the same segment? Well, possibly they might be. I mean, A and B might be on the same segment, but actually A might be on one network and B could be on another network. These are private addresses and they're shared across the internet. And this is just one example. In general, the fact that you're on the same subnet, and this is of course /16, from one of those IP subnets that we learned belong to the private addresses. So even in that case, you can't know for sure that they're on the same segment. What about the other case? Let's say A has the address of 192.168.0.1 and B has the address of 10.0.0.3. Does that mean they are 100% not on the same segment? No, I mean, a segment is a second layer concept. You could have here a switch. They could be connected directly to one another. A and B are one hop away, even though they reside on different subnets. There is no really good solution here. Every solution would have some flaws. What all modern OSs, at least all the modern operating systems that I'm familiar with, assume is that indeed if you are on the same subnet as me, then you're on the same segment. This might not be the case, and then it sometimes causes headaches for the AT people, but it makes for a way more dynamic way to just add someone to the same subnet. Would mean that by default, the operating system would assume it's on the same segment as you. Let's see how that works in action. Let's see this network. We have C0, computer 0, behind this router, and C1 on the other end. There might be other routers here, but for simplicity's sake, let's just assume it's a single router. Now, if we look at the network structure, that means that we have two different segments here and two different subnets. So the first network on the left, the gray network, has the subnet mask of, let's say, 111/24. So everything that starts with 111, and the C0 has the IP of 1113, whereas the router, that is this specific port of the router, because it's a router, which means it has multiple ports, one in each network it connects. So on the gray network, its port has the assigned IP of 1111. Also have the other network here, where the router on its other port has the IP address of 3331, and C1 has the IP address of 3332. This might be a subnet mask of /24, even though, of course, in both cases, it could be /8, /16, /20, it doesn't really matter. What does the process look like? So let's say everything rebooted, there are no caches now. So all of the ARP caches of the computers as well as the routers are empty. And C0 now wants to send a ping to C1. By that, I mean using the IP address of C1. So what does C0's operating system need to understand? As we said in the previous slide, it needs to separate between the case where C1 resides here within the same segment and the case that it resides here on another segment. And to do that, it asks whether the IP address of C1 resides within the same subnet as of C0. The answer is, of course, no. Since it's not the same subnet, the operating system assumes they're not on the same segment, which means C0 would need to route the packet through the router. So the ping packet would have to go first to the router and then to C1. So for that, C0 needs to know the address of the router. Now, how does C0 know what its router is, what the IP address of the router is a question that will be answered on a future slide. But for now, let's say C0 knows that the IP of the router is 1111. So what's the next step? C0 knows it needs to send the packet to the router, to this port of the router, to the one corresponding to the IP address of 1111. So what does it need to do? It needs to know its MAC address. How does it figure out the corresponding MAC address? It sends an ARP request. The ARP request is sent in broadcast. It might look here as unicast, but what I mean by that, it's broadcast to the entire segment who has the MAC address that corresponds to the IP address 1111. The router is liable to reply, but even before it does, the router will learn something important here. It learned that the IP of C0 is 1113, and its MAC is the MAC of C0. I'm not going to write here full MAC addresses, but just say the Ethernet address of C0. How did it learn it? Because it appears in the ARP request, as we've seen when I opened Wireshark. So this is stored in the cache. Okay, so now the next step is for the router to reply with an ARP reply that is sent by default as unicast, so to the Ethernet address of C0, the MAC address of C0 that the router has just learned. In this step, C0's cache also includes the dynamic entry that the IP of 1111 corresponds to its MAC address. Notice that the MAC address of 1111 is different from the MAC address of 3331. They're the same router in the sense that it's the same box, but it has two different network interfaces, two different physical ports on the router. Now we're going to send the ping, and this hop, it's going to be transmitted from C0 to the router. Try to fill in these values with me. What's written in the source IP of this ping? So the source IP would be 1113, that of C0. And the destination IP would be 3332, that of C1. That's an important thing to see here. In the IP layer, it goes from the first hop to the final destination. So the IP layer, what I marked here in blue, is actually this kind of arrow here. It's all the way from source to destination. What about the MAC addresses, the Ethernet layer? Here, the source MAC would be that of C0. How does C0 know it? It was manufactured with it. That is, the network interface card was manufactured with it in the factory. And the destination MAC was just now learned by C0 in the ARP process. So here we would have Ethernet of, say, router in leg 1. So let's mark it R1. We can mark this port as R1. So while the network layer, the IP layer in this case, shows the process or the path from C0 all the way to C1, Ethernet layer, the second layer, the data link layer, only shows us one single hop. And that's exactly what these layers are supposed to do, right? The second layer is responsible for transmitting data between two hosts that are directly linked, that is, they are linked via a single hop like C0 and the router. And the third layer, the network layer, is responsible for transmitting data over multiple hops. So that's exactly what we can see here in the addresses within the same packet. So if I were to look at this packet on Wireshark, in the Ethernet layer, I would see C0 to R1, whereas on the IP layer, I would see C0 to C1. I think that's really cool. Okay, now the router receives this packet. What would be the next step? So the router would need to transmit the packet, forward it to C1. For that, it needs the MAC address of C1. How is the router going to get it? It's going to get it by using ARP. Again, so it sends a broadcast message, an ARP request asking who has the corresponding Ethernet address of the IP address 3332, and C1 would provide an answer. Before the answer, C1 can learn the IP address and MAC address of the second port of the router, say R2, and store it in its ARP cache. For future packet, for example, when it's going to respond with the PONG packet, the echo reply, it might use that information that's already in the cache rather than having to send an ARP request on its own. So after storing it in the cache, C1 can reply with an ARP reply, whereas the router learns that the IP address 3332 is associated with the MAC address of C1. At this point, all the ARP caches are filled with the relevant information, and now the router can forward the packet over to C1. So what does the packet look like from the hop from R2, that is the right port of the router, to C1? What do you think? What would be the source IP address? So marking it again with blue, the source IP is 1113. It's that of C0. Again, the IP layer, the network layer, shows me the entire route from C0, from source, all the way to the destination. All the way to the destination. That's what we can see on the third layer. So the source IP is 1113 and the destination IP is 3332. What about the MAC addresses? So the source MAC is going to be that of R2, that is the port of the router, which belongs in the same segment as that of C1. And the destination MAC is going to be that of C1 that the router has learned via ARP, the address resolution protocol. So again, we can see here that the network layer is responsible for a source to the final destination, whereas the second layer, via its addresses, shows us that it's responsible for a single hop, in this case, this port of the router and C1. And what we have here is we have a really nice way to see it in a single packet. Notice that the IP layer actually hasn't changed. That's not exactly accurate, but the addresses haven't changed from hop to hop. What did change was the Ethernet addresses. What is going to change, by the way, between R2 and C1? What's going to be different from the hop of C0 to the router? So of course, the Ethernet layer is different. So the checksum in the Ethernet is different. What about the IP layer? What's going to change? Think about the IP header that we saw before. What fields will change? So first of all, the TTL will change. It would be reduced by 1. So if here the TTL were 128, then on this hop it would be 127. As a result of that, the header checksum would change as well. So these two fields do change between one hop to the next, but the addresses don't change. There is one exception to that regarding the private addresses, but we haven't addressed that yet. So for now, we're assuming all IP addresses are globally distinct and unique, as was supposed to be the case. So what does a routing table look like? Routing tables exist on your machine, your device, which has network interfaces. It also exists on the router or other network devices with a network layer. Let's look at one by the operating system. Okay, so I open the command line here, and I'm going to type route print -4. The -4 is to say I only want IPv4. The -4 is to say I only want entries from the IPv4 routing table, not the IPv6 one. All right, we can see here that I have 3 different interfaces. If we look at the interface column of this table, you'll see 3 distinct addresses. We have this one here, starts with 192.168. That's one interface I have. You have 127.0.0.1, which, as you know, is the loopback interface. So again, anything that starts with 127 could be a loopback address, but the loopback interface by default in most operating systems, if not all, is 127.0.0.1. Next, we have this one, 172.28.161. They appear multiple times, but just so you see, we have 3 different interfaces. So when we send a packet over the network, it would go through one of these interfaces. That's the interface we're sending the packet from. What we see here is a list of rules that are sorted by specificity. So the most specific rule is the bottom one, and then it gradually grows up to the most generalized rule. Let's see an example. So let's say we want to send the packet to the address 172.28.165. Where does that go to? All right, let's see. We'll go one by one. We're looking at the first, 3 entries here. Each one has the network destination of 255.255.255.255 with a subnet mask where all bits are on. In other words, this network includes exactly one address, this address, which is the broadcast address. Does this address belong to this network? Of course not, so we keep going. The next 3, these 3 are all multicast addresses, and our address does not belong there either. Here we see something a bit interesting. We can see that we have, as a rule, the broadcast address of this specific network. So our network is Y92.168.3/24, And this is specifically the broadcast address of this network. If you send something to this broadcast address, it will go to this interface. But that's not the case here. We're not sending to this broadcast address. Let's keep going to the next one. So the next rule here, 192.168.3.155, this is the actual address of the interface, as you can see. We're not sending anything there either. Now we have a rule for the entire subnet. This says if you send any packet whatsoever to 192.168.3, whatever it is, that is /24, as you can see here, we have 255, 255, 255.0, which is like saying the most significant 24 bits are on in the subnet mask, that is, they're part of the network ID. So any packet that would be sent to any address starting with 192.168.3 as its first 3 bytes will be sent on link to 192.168.3.155 interface. On link means it's on my segment. Same segment, you just send an ARP, you get a response, and then you transmit directly. You don't need to go through another router. But our address, the one here, is not within this network. So we keep going. Let's keep it up. So 172.28, 175.255 is again a broadcast address of this specific network, but we're not there either. 178.28.161, all bits are on. Again, an address of the network interface itself. It's not us. And here, look at that. We have 172.28.160, 0, 255, 255, 240, 0. Are we part of this network? Well, that's not /24. We could compute what it is, but we already exercised that on previous slides. If you feel like you need more exercise, please try to convert that to binary, see how many bits we have here. You can post your answer on the comment section below. But for now, I think it's pretty clear that the address in question does reside within this network. In that case, the rule that it matches is this one. So the packet is going to be transmitted on the interface 172.28.161, and on link, again, an ARP would be sent for this address, and then given that we get an ARP reply, we will transmit the packet directly. What happens if we send a packet to, say, 1, 2, 3, 4? Let's check, again, going from the most specific. So it's not one of these addresses, neither is it in those networks. Not here, 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 not here. Ooh, this is interesting. Look, it's 127.0.0.0 with a subnet mask of /8, right? So this rule right here is telling us that everything that starts with 127 will go to the loopback interface. By the way, not the address in question, this one. So it doesn't belong in any of these networks, so it will belong in this one. This rule is the default rule, because every address resides within the net mask of 0000. It means anything goes, and it has a gateway. This is the default gateway. So any address that doesn't belong in any of those rules will get directed to our default gateway. That's why it's called the default gateway. It will be routed to this default gateway on this interface, and then our gateway, our router, will then forward it to its destination, possibly via another router. As we said many times, the network layer is responsible for transmitting packets between hosts that are not necessarily directly linked. That is, they may be linked by more than a single hop. This entails a few things. One of them is that there may be different second layers in the middle, and each one might have a different hardware, which might come with a different MTU, or maximum transmission unit. What does that mean? So if you remember, for example, when we talked about Ethernet, we said that the maximum length of an Ethernet frame is 1500 bytes of data. So if we have here a red network, that's an Ethernet network, and let's also leave some space for a router here. That's an Ethernet network where we have the computer A and some other computers perhaps. And we have a switch to connect different devices. And everything here is using Ethernet. Now, the fact that you Ethernet with an MTU of 1500 bytes of payload of data, that is without the header and trailer of an Ethernet packet, that means that if A has a message that is longer than 1500 bytes, it would have to split it. But as long as it's 1500 bytes or less, it can be a single frame in the Ethernet layer. So let's say that A has a message to send to B, and B is here in the blue network. And this router here actually is not really red, it's not really blue, it has a red port on the red network and blue port on the blue network. And here, this is something else. It's a different kind of protocol, let's say carrier pigeons. All right, so in order to route the packet from A to B, it has to go through this router. And in the second hop from the router to B, it goes on an AVM carrier, let's say a pigeon. Then this specific breed of pigeon, say, is a bit weak, so they can't carry over 1400 bytes. So let's say the MTU here is 1400 bytes. Now, of course, this is a simple example. I don't really claim that different breeds of pigeons can carry different amount of bytes, if that even makes sense, but bear with me for the example to make it more interesting and entertaining even. So what is the router supposed to do when it receives that frame? So let's say A is sending a frame. This frame is exactly 1500 bytes long. And the frame is sent, being transmitted over the switch to the router. Now the router receives it, and it can't transmit 1500 bytes to B. The hardware, the second layer, in this case, the pigeon can't carry as much in a single frame. So the router would have to split the packet or fragment it into two separate fragments. Now, there are a few things we need to remember when we do that, and those things all relate to this pretty line within IPv4 header that we skipped, and I promised you we'd get back to it. So here I'm fulfilling my promise, and we're going to get to every bit here. And by the end of that, you will have known every bit and byte within IPv4 packets. So what does it mean to fragment a packet, to split it into fragments in a way that makes sense? So think about it like so. Let's say we have here A, and here B, and another example, let's say here we're talking about an Ethernet, so the MTU is 1500. And here we're talking about some other network where the MTU is larger, say 1600. And let's say A now sends a packet. And the packet is 1600 bytes long. And it gets to the router, and the router has to split it. And then A, let's say, even sends another packet. Let's mark that one in orange, and let it also be 1600 bytes long. And let's say that the router, when it receives the first packet, let's call it packet 1. So when the router receives packet 1, it has to fragment it, to split it into two fragments. So let's say it fragments it like this, and we have here now two fragments. We have P11 and P12. And then when it receives the second packet, let's call it packet 2, it also fragments it here, and we have the packet 2 fragment 1 and packet 2 fragment 2. Now when the router receives the packet and sends the fragment after fragmentation, remember that the order here is not guaranteed. As I mentioned, IPv4 is not a reliable protocol, so it doesn't guarantee the order of receival by the end party. So when B receives the fragments, it might receive it in various orders, and it might get, say, packet 1.2 first, that is the second fragment of packet 1, and then get packet 2.1, that is the first fragment of packet 2. We don't want, when B receives it, to reassemble or defragment this packet in a wrong way. And a wrong way could mean different things. It can be that it has here, let's say, P1.1, and it can have here P2.2. So taking different parts of different fragments. It could also be a different order. Say it could reassemble P1.2 and then P1.1. Any combination that is not saying it's one packet of P1.1, P1.2, and the other packet of P2.1, P2.2 is completely wrong. So we need to account for all of these things. To do that, we'll take a look at that line within the IPv4 header that we've neglected so far and give it some importance. So the first thing here is to be able to know that both of these fragments, the red fragments, belong to the red packet, to packet 1 and not to packet 2. To avoid a case where you reassemble a fragment from P1 and another fragment from P2 as being a part of the same packet. Now, to be part of the same packet, two fragments must share the same source IP, the same destination IP, the same protocol field value. For example, both need to contain a TCP segment, and the identification field is especially for that. We have 16 bits here, so a number between 0 to 65,535 that identifies the packet. So, for example, let's say P1.1 and P1.2 would have the same ID, short for identification, of say 1337. So if it will be 1337, this one will also have the ID of 1337. Good. So this solves the need to know that different fragments belong to the same original packet. Of course, for that to really happen reliably, we need other packets that are sent in the adjacent time to have different ID values. For example, P2 here would have the ID of 1338. It doesn't have to be a close value. Different operating systems do this differently. All right. So we solved the problem of knowing which packet a fragment belongs to. Now, there are other issues here. Another problem is to have, for example, P1.2 and then P1.1. That is, both fragments do indeed belong to the same original packet, but they're reassembled in the wrong order. So for that, we have the fragment offset field, which has two interesting facts about. So an offset means an offset in bytes from the beginning. So the first fragment will always have the offset of 0. So here the offset will be 0. And for the second one, it will be the offset in byte, but there is a caveat here. Those of you who looked carefully might have noticed that, especially on the previous slide where it was evident, that this field is actually 13 bits long, which is a bit problematic given that the total length field is 16 bits long. Now, if an IPv4 packet can have a length of up to 2 to the 16th power minus 1, how can the offset be only until 2 to the 13th power minus 1? So to resolve that, the number here is actually divided by 8. So for example, if the first fragment had, say, 80 bytes, then the offset of the second one, which starts with 80, byte 80, would actually have the value of 10 here, because it's divided by 8. We'll see another example later, so I'll make sure it's clear. All right, so this solves the problem of knowing which fragment comes first, but there is another curious thing here. Why would I use an offset and not a sequential number, like I did here, 1 and 2? I could have fragments numbered sequentially, 1, 2, 3, 4. Why do I need the fragment offset? Again, I encourage you to pause the video and think for yourselves. So there are different reasons, and some of them are reasonable, but there is one really essential issue here. And the issue is this. No one really promises that there is only one router between A and B. The different packets can even travel between different routes. Now, let's say one of the routers here in the middle, say the green router, has an MTU within a network here of 1200. what happens now? I mean, the router will receive a packet that was fragmented. Say the first fragment is 1500 bytes long. What is it going to do with it? It's going to fragment it, right? And what would happen to the fragment offset? It's already a fragment. So let's say we had fragment 1, and now we need to further fragment it to additional fragments. What would it be? Fragment 1.1, 1.2? What would happen on the next fragmentation? So to avoid that, we simply have a fragment offset. So if we fragment it further, still each fragment gets a single fragment offset in bytes from the original beginning of the original packet. All right, so this is the fragment offset. In addition, there are 3 bits here. One is reserved, always set to 0. There is a small caveat about that I'll address in a future video. But for now, let's say it's just reserved. And the reason to have such bits that are reserved that we don't know what we don't know when we publish the protocol, right? They published IPv4 back in 1981. Lots of things have changed, of course, and they wanted to leave this additional bit for, say, reassurance. So if they find out that something comes up that they haven't thought about, they will have this flexibility of overriding this bit. The other 2 bits here, one is DF. DF stands for don't fragment. So if this bit is on, it means that the router that receives the packet, let's say we're sending here a packet from A to the router, and the DF flag is on, and this packet is 1600 bytes long, and the router can thus not forward it without fragmenting it. If the DF flag is on, it means the router, don't fragment it, just drop the packet. Perhaps send back an indication that you've done so, but in any case, do not fragment. The other bit here, called MF, for more fragment, tells us whether this specific fragment is the last one within the packet. So if, say, we have this very large packet that gets fragmented once, twice, and more times, then all of the fragments, with exception of the very last one, would have an MF of 1. Yes, there are more fragments coming. MF equals 1, MF equals 1, and so on. The very last one would have MF equals 0, which means there are no more fragments on the last fragment. And notice, since again in IP, it's not guaranteed that you receive the fragments in the order they were sent. You might actually receive this fragment first or second or not last. How do you know? Given the fragment offset, you know how to put it in memory. Another good reason to have an offset rather than, say, a sequential number for fragments is that you could build the packet in memory by the fragments you get. So let's say we have all of these fragments, and I first receive the last one actually. I can put it here in memory, and then I receive the second one, and I know that it's here and not anywhere else. And the fact that I know it is because I have its offset. So I know that it starts at, let's say this is 1200 bytes. I can put it here, and then there is some length. I can put it here in memory, so I can allocate all of this buffer in advance and start filling it with fragments as they cool. So what I want to do with you now is not just an exercise in fragmentation. It's an exercise in how we validate our understanding of a concept we've just learned. Let's say you were just to read this in the IPv4 RFC 791, and you'd say, okay, I think I understand how fragmentation works. How would we actually put this to the test? Now, the way to do it is to try to think of what these values should be on your own and then validate that. So let's do just that. Let's say that we have this scenario where we have, again, A sending a packet to B. So we have A, and the network that A is attached to has some MTU, let's say 1600. And B is actually Ethernet with an MTU of 1500. And A is going to send the packet to the router with 1600 bytes. And now we want to know what the router would do, what the fragments would look like. So from what we've learned, Let's see. We have two fragments, fragment 1 and fragment 2. So we take this 1600 long, this 1600 byte. So we take this packet that is 1600 bytes long, and we fragment it here. What is here, we'll talk about it in a sec. So what's the total length that we can have? What's the maximum total length we can have for the first fragment? If this is an Ethernet network here, remember that we're talking about this hop here. So what's the total length going to be? For the first fragment, it's going to be 1500. I want to send as much as I can. What the header size is going to be? What's the length of the header? So we have 1500 bytes in total. How many is the header going to take? At minimum for IPv4, it's going to be 20 bytes. This is the minimum size of an IPv4 header. And as I told you before, it's by far the most common value you'll see in the header length field. So we have 20 bytes of header at a total length of 1500, which leaves us with 1480 bytes of data. What about the identification field? Well, we can't know in advance, right? It's something that the operating system is going to perhaps randomly generate, or not randomly, but we can't know in advance. The important thing is, let's say we have the value 24601, then the important thing is that, help me out here, try the second fragment is also going to be 24601. So these two have to match, which conveys the information that both of these fragments actually originated within the same original packet. Okay, back to the first fragment here. What's the mth bit going to be? It's going to be 1 or 0. It's going to be 1. Indeed, there are additional fragments, specifically an additional fragment coming. So this is going to be on, and the offset for the first fragment is always 0. Good. Now let's look at fragment number 2. So for fragment number 2, what's the total length? Actually, it makes more sense to start with the data. So we wanted to send 1600 bytes of data, which means that we will send here, if we already sent 1480, we have 120 bytes left to send. We'll also send the header, which is, again, minimum 20 bytes, which means the total length is going to be 140 bytes. So again, we have the header of 20 bytes, the remaining data of 120, calculated by saying that 120 plus 1480 is 1600, what we were originally trying to send. Overall, we get a total length of 140. The idea is the same as of fragment 1. What about the MF bit? It is off. Now for the offset. So what is the offset here? So we sent 1480 bytes so far, so the offset is 1480. However, remember that since the fragment offset field is 13 bits long, so 3 bits shorter than the total length field, we divide that value by 8, by 2 to the third power. So the 1480 divided by 8, we get 185 in decimal, which is in hex B9. And I'm saying that in hex because we're going to open Wireshark soon, of course, to validate this hypothesis. And there, that's the value we'll probably see because Wireshark, at least in most versions, writes the information in hex and not in decimal. All right, let's start Wireshark and give it a go. Okay, so I'm going to start a new sniff on Wireshark. And I open the command line here, and I'm going to use ping -L. -L allows me to specify the number of bytes that are going to be sent in the buffer of the ping request. Now, ping actually runs over a protocol called ICMP, which has a header of 8 bytes. So to get to 1600, like in our example, I will need to say 1592 bytes of data plus those 8 bytes of header of ICMP. And let's just ping Google, because why not? So I'm pinging Google. Back to Wireshark. I don't really care as much about the reply I get or don't get from Google. Now, one thing to notice, I used Control E to stop this sniff, and it will be pretty hard for me to find these fragments or this packet by just browsing here. So I can do various things. I can write ICMP. Another thing I can do is, and I'm using this opportunity to allow us to learn more about Wireshark, is to go here to the IPv4 layer of any packet that I found that has IP and say here for the flags, take the more fragments, because we're going to have one fragment with the MF bit set. So I'm going to apply this filter and say not selected. That is, I don't want packets where MF is 0. And look what we found here. We found here a fragmented IPv4 packet. Now it doesn't tell me what it is exactly, because to see what it is exactly, we're going to see the other fragment as well. But I can see the number here, 62297. So let's clear the filter now. And look, we have two fragments here, and you can see here the packet is an ICMP echo ping request. But that's not the interesting part for us. This interesting part is to actually look at the different fields. So again, we're looking at IP. Let's look at the header. So we have here the version set to 4. Not surprising, right? The header length 20 bytes. And notice that it says in parentheses 5. That is, 5 is what's actually written. This is the binary form. But Wireshark knows that you have to multiply that by 4 to get 20. The next field is that of type of service, also called differentiated services field, as you can see here. And then we have total length. Total length, as we said, is 1500, which is the maximum you can get for the payload for the data of the Ethernet frame. And the identification here is 2583. Now, we don't need to really remember it or something. We'll just make sure it's 2583 on the next fragment as well. Regarding the flags, so the reserve bit is not set, or fragment is not set. We do have more fragments bit set, as we assumed, and we have a fragment offset of 0, because this is the first fragment. Let's quickly also look at the other fields here. We have a time to live of 128. That's the actually hop count. As I'm running this from a Windows machine, the default value is 128. Protocol ICMP, that's the payload, the ping echo request in this case. The value is 1 for ICMP. Header, so the header checksum here, it says 0, validation disabled. This confuses lots of people, so I do want to dedicate a moment to talk about it. So first of all, you see here those square brackets. This means that this is something that is not sent on the packet, this information within the square brackets. This information is something that Wireshark tells us in addition. And here it says validation disabled. This actually means that the operating system doesn't really validate the checksum of the header. Rather, it's something that's done by the network interface card in the hardware level, so that when it gets to the operating system or to Wireshark, you get that as zeros. Not super interesting for us now. It's an optimization. It kind of breaks the layer model because the network interface is, strictly speaking, a data link device and not a network layer device. If you're interested in that, just ask me in a comment and I'll provide more information. And then we finish this up with the source and destination addresses. Cool. So what do we expect from the second fragment? Again, we want to see a total length of 140 because we still have 120 bytes to send and 20 bytes of header. We expect the same value in the identification field, that is the 2583 that we see here, and we expect the flags to be all 0, more fragments specifically 0, and the fragment offset will be B9 in hex or 185, which is 1480 divided by 8. So let's look at the second fragment. And what do we see here? So indeed, we have a total length of 140, as we expected. The identification field is 25A3, also as expected. Regarding the flags, this bit is off. Fragment offset, it says here 1480. Was I lying to you? Does it really say 1480 in the actual data? I don't think so. How would I know? So one way is to read the binary. Another is to click here on this field, and you'll notice that when I click on it, you can also see that it's marked on the right-hand side. So right here, and it says B9, and B9 in hex is 185, as we said before. All right, so now we know a few things. We know how to filter with Wireshark, something we covered in the past, but refreshed our memories about now. We know how fragmentation works in IPv4, what it is for, and what the different fields mean. And in general, we know what every bit and byte in the IPv4 header actually mean. Now I'd like to introduce you to another protocol, so not a part of IPv4, but an adjacent protocol. If you recall, IPv4's RFC number is 791, ICMP's RFC number is 792. So as you could guess, they were created around the same time and as part of the same suite of protocols. ICMP stands for Internet Control Message Protocol, and it's mainly used for debugging, that is, by our beloved IT people. As we know, we love our IT people. We want their lives to be as good as possible, and we love giving them tools to debug networking issues when they occur. One of those tools is ICMP. ICMP is used for various things, and it has a type for the message. So I wanted to introduce you to the message types and what they actually mean. First option is destination unreachable. That means that I sent a packet, let's say I'm A, and I have a router X. And this router receives a packet from A, and the packet has a destination address of 1234. Now, if the router doesn't know how to route to this address, that is, it doesn't have a routing table entry that matches this address, as we saw in the routing tables before, so it doesn't have a default gateway rule and no rule captures this address, it doesn't know how to route it. It's supposed to reply back saying destination unreachable, I can't route to this destination. The second message type is time exceeded. So it's not really timed. It's related to the field TTL, that is time to leave, which is actually hop limit. So the hop limit exceeded. So if say A sends a packet with a TTL of 1 and the router receives it and it can route the packet to its destination, but now the TTL here is 0, then the router drops the packet, and it could also send an ICMP message indicating that that's what happened, that is a time exceeded message. The third message type I want to cover is parameter problem. Now that means you had some issue with the header. For example, let's say the IHL, the field that conveys the length of IPv4 header, if you set it to 4, that's a problem. Why is 4 an invalid value? Because as you know, the minimum size of an IPv4 header is 20 bytes. And if the minimum is 20 bytes long, then you can't have 4 times 4 because in the word 16, it's just an invalid value. It doesn't mean anything. So you would get back a parameter problem packet that is an ICMP that tells you there is a parameter problem. And when I say an ICMP packet, just to be clear, would first have the second layer here. It could be Ethernet, it could be Wi-Fi, Bluetooth, whatever. Then we would probably have IP. Let's stick with IPv4 for this example. And yeah, it would be IPv4 if it's ICMP for IPv4. And then would have ICMP on top. So ICMP is the payload of IP, and we actually saw that in the fragmentation example. All right. The next packet is source quench. Now, source quench is a way for the router to tell a host, listen, you're choking me. There is a lot of congestion on the network, too many packets that I have to process. I can't process so much. Please slow down. Don't send me so many packets. So let's say now A sends the packet to this router. Let's call it R1. And then R1 sends this packet to R2. And R2 is getting busy. It feels congested. That is, it receives too many packets per second than it can process. And it sees that, say, A sending too many packets a second, too many packets too fast. So the router R2 can send the packet back to A and saying source quench. In other words, dude, you're choking me. Stop it. Just stop sending data. Slow down. Either don't send data or send data from another route or send your data, but more slowly. This message could also be sent between routers, not necessarily to end devices. The next message type is redirect. Redirect is me as a router, for example, receiving this packet from R1. And I look at the packet, I see it destined to 1, 2, 3, 4. And I say, hey, R1, you know what? Actually, to get to 1, 2, 3, 4, you could have gone through here. You have router 3, it's another route that can also communicate with 1, 2, 3, 4. So I'm teaching you about a new route that exists now in the network. Echo is ping. You send an echo request, you expect to receive an echo reply. That's the easiest way to make sure a machine is up, that is not shut down, available and responsive, so you can reach it via IP. You can route your packets to it and you see a response. If you don't see a response, then you need to start debugging what's happening. If you also want to know the timestamp, the time on the other side, you can set a timestamp request and then you would get a timestamp reply. It's almost exactly the same as echo request and reply, just with the addition of a timestamp. So I've just started sniffing, so we can see an example on Wireshark. I'm going to start the command line, just ping 8888. I get some responses. Back to Wireshark, I'll type in ICMP as the display filter. And we see here the ping request, echo request, and reply. Let's look at the packet. So as I mentioned before, we would have Ethernet, then IP. The protocol type within IPv4's header is going to be 1. 1 says this is an ICMP packet as the payload. And now if we look at the ICMP layer more closely, what do we have here? So it starts with a type. The type is echo request, and the rest is dependent on the type. Everything else stems from that. For example, here you would notice that there is some sequence number. And why is that important? Can you guess just from looking at this packet? So indeed, Wireshark even found the response frame. And to find the response frame, and I can click here, it would take me to the response frame. It knows that it is the response frame because it had the same sequence number. You can see here that this one had the sequence of 246144. And this one also had a sequence 246144, just that the ping is with reply. By the way, a cool trick to see that, let's say I'm not sure if this sequence is really interesting. What I can do is I can add that. I can use right click, apply as column, and then I get that as an additional column in Wireshark. And I can see here the request reply have the same value. Then the request reply, the same value, request reply have the same value. Let's see if it also matters for the rest of the sequence number. So again, right click, apply as column. Yep, 6144, 6144, 6400, 6400. All right, now let's say I don't know if the identifier is also important here. The fact that it says 1, is it meaningful? I'm not sure. Let's add it as well. All right, I see all of them have the identifier of 1. So just from looking at that, I'm not sure why it matters. It doesn't help me identify the request and knowing which response is sent for each request. And it's not really important for me that we cover this now. I just wanted to show you what ICMP actually looks like and use this opportunity to show another cool trick of Wireshark, that is applying things as columns. One very cool utility that is both useful and interesting to understand how it works is called traceroute, or traceRT as the command from the CLI. If you want to run it, you can use traceRT -4, which means force IPv4 rather than IPv6, -D to bypass DNS resolving, which we haven't learned yet, and then the destination like google.com. In this example, this could also be an IP address. So if I want the DNS server of Google, I can do 8888. Either would work. What's going to happen when we use traceRT and why is that useful? So let's say we send a ping to google.com and we get no response. So if Google doesn't respond, it might mean many things. It might mean that we are not connected to the internet at all. Maybe we can't reach the first router. Maybe the route to google.com from a router is problematic. Maybe it's the second router that is problematic. So in order to understand that, we can use traceRT. There are other ways to do that too, but I wanted to focus on traceroute because I think it shows a good example of a few things we covered in this lesson. So what does traceRT actually do? TraceRT exploits a very specific trait of the IPv4 header in order to find all the intermediary routers between the source machine and the destination machine. So if we have R1, R2, R3 and their IP addresses, we want to find out who they are. How can we do that with things we've learned so far in this video? Can you guess? Well, one way would be to send a packet to google.com. It could be any packet. Now, traceroute uses an echo, ICMP, echo request by default, but it can be any other packet over IP. So we send the packet. We set the destination to whatever we want. Let's say 1234. That's the IP of Google. It's not the IP of Google, but just for the example. And we provide a TTL of 1. What does that mean? When the packet reaches the first router, the router is going to change the TTL, decrement it, so it will be 0, in which case it needs to drop the packet and send a reply to the source computer, let's call it A, to send a reply, an ICMP TTL exceeded, time exceeded, which will include in its source, so let's give it another color. Let's do this in blue. So this packet here is going to be ICMP time exceeded, sent from the IP of R1 to the IP of computer A. Again, this is A. So when A receives this ICMP time exceeded packet, it learns that the IP of R1 is the IP of the first hop on the way because it is the one that responded when it sent the packet with a TTL of 1. And it can also time the RTT, the round trip time, that is the time it takes for a packet to travel to R1 and back. Since this is the time since A had sent the packet with the echo request, the red packet here, till it received the response of the ICMP time exceeded packet. Using DNS, we can also resolve the name of R1 if it has such a name and if it responds to DNS resolving, but we'll learn that in another video. So for now, we just say that traceRT displays the name by default when possible, but we'll cover how it does that in another video. Cool, so we found out R1. How are we going to find R2? Indeed, we'll send a very similar packet, but instead of writing here 1, so instead of 1, we'll write here 2. So we send the packet with a TTL of 2. When R1 receives it, it sends instead of TTL 0, it sends a TTL of 1. It decrements the TTL to 1. And then it sends the packet here with the TTL of 1. When R2 receives the packet, it will decrement the TTL again to 0. And when it reaches 0, it means it has to send back an ICMP time exceeded packet to A. Of course, it will go through R1 in the process, saying time exceeded, and the source here would be that of the IP of R2. In this way, A can learn that R2 is the second hop between itself and google.com, and it can learn how much time it took by sending this packet and timing how much it took for the response to be received. By default, traceroute sends 3 different packets for each hop, that is for each TTL, so 3 packets with TTL of 1, then 3 packets with TTL of 2, in order to time 3 different times the time it took for the packet to be received in the intermediary router and back at the source machine, so that you can see the difference or variance among them in case there is such variance. We can keep on like that using the TTL of 3, 4, and so on until the reply we get is that of google.com or 1234, the destination, the final destination that we sent. This way, by using ICMP that we learned, specifically for the response, not necessarily for the request we're sending, as well as exploiting the TTL field and very carefully incrementing it one by one each time, we can find out all the intermediary hops between the source machine and the destination machine. One perhaps quite clear drawback of this method is that when we send a packet from A to Google, it might go through one route, but the next packet might go through another route. That is, different packets can be routed in different routes. This is basically a trait of IP, which is a stateless protocol, and using packet switch kind of network protocol. I talked about it in a previous video about different implementations of the network layer. Since this video is getting quite long, I didn't want to cover that again here, but you can find the link in the description below to that video as well. In short, it means that we don't have a connection between A to Google.com in order to send packets. We just send each packet at a time, and each packet is being routed potentially individually and independently of the previous packets or future packets that are routed to the same destination. Okay, in order to finalize our talk of IPv4, I want us to introduce to one more protocol, which helps us answer a very fundamental question. That is, how do we know what our IP address is, and what our subnet mask is, and what is the IP address of our default gateway? So all of these are answered by a protocol called DHCP. DHCP stands for Dynamic Host Configuration Protocol, and it allows for assigning addresses dynamically rather than statically. So I don't have to say this machine always gets this IP address and another machine always gets this IP address. Think of a world without dynamic allocation, but static allocation. How could that work? So for example, let's say I have a network with a few machines. They're all connected via the same cable. For simplicity, I'm not even going to draw an Ethernet switch here or something. So we have a few stations here. We have A, B, C, D, and E. And now A wants to know its IP address. So one way to do that is to have some kind of server here. And when A, say, boots for the first time and it needs an IP address, it sends a broadcast message. So broadcast to all machines here saying, hey, this is my MAC address. What is my IP address? In that case, the server has to have this mapping. So it holds this kind of a table saying that for these MAC addresses, these are the corresponding IP addresses. So for the MAC address of computer A, which says A, and so on, the IP address would be 24601. So A would ask, as broadcast, it doesn't know the server yet, what is my IP address? This is my MAC address. The server will say, oh, this is your MAC address, so this is your IP address. I know it, and will respond in unicast. Does this look familiar? It feels very much like ARP, Address Resolution Protocol, which helps us resolve an IP address to its corresponding MAC address. This is exactly the reverse, and this protocol is indeed called RARP, for reverse ARP, which is good and all, but it has a few main drawbacks. The one that stands out the most is that this is static. So except for being wasteful, we might not always need all of these addresses here. It means that when you add a new machine to this network, someone needs to fill this mapping at the server, and that someone is our beloved IT person. So the poor IT person has to go all the way to that server and again configure something manually. We don't want that. In addition, since we have that request being sent in broadcast, it means that you need this server for the segment, because by default, broadcast addresses, broadcast packets or frames are sent within the segment. So for every segment of the network, you would need a ARP server, which is very wasteful. So this protocol was used in the past, but we haven't had DHCP for many years, and DHCP allows for dynamic allocation. So we don't have this static mapping. We do have a mapping, and DHCP runs as a fifth layer protocol on top of UDP, on top of IP, so it can cross across segments. We'll talk about that when we learn more about the fourth layer and the fifth layer. So how does that work? Let's continue with assuming it's a single segment for now. Now at this point, we don't have RAR, but we do have a server, a DHCP server. And A, when it puts, still needs an address. So it sends a packet called a discover packet. So now it's sent from A, and this is a discover packet. The discover packet is sent asking, hello, I'm a new machine on the network. I don't have an IP address. Help me discover DHCP servers, potentially more than one. When this packet is sent, what's the destination address going to be? The destination address of the packet is going to be broadcast 255, 255, 255, 255. And why is that? It's because A doesn't know who the DHCP servers are. This is for the very first time A receives an IP address on this network. There is a different process for ensuring you have this IP for longer. I'll talk about it later. All right, so it's sent to the broadcast address, but what is used as the source address? So the answer is 0000. If you remember from the previous slide, we mentioned that this just means this host. A doesn't have an IP address yet, so it sends 0000. Next, the DHCP server, or potentially multiple DHCP servers, reply with a response. This response is called an offer. DHCP server or servers offer to this machine a few things. What things? So let's write in more info here. So an offer could look like this. This is the IP address that I propose for you. You can use this if you accept. This is your subnet mask. This is the default gateway. This is the DHCP server. This is the DNS server. We'll learn about DNS in a future video, and basically everything you need to know in order to be a functional part of this network. The offer is sent from the DHCP server's IP address. So this is from the DHCP server. Again, there could be multiple servers. You would get multiple offers. What address is it being sent to? So we can't send it to 0000, as it doesn't mean anything. We can send it to A's address because A doesn't have an address yet. Thus, it's sent to broadcast. So all machines are likely to see this packet, but only A is supposed to actually listen on DHCP at that point and process this packet. Cool, so we sent the discover, we received an offer or maybe multiple offers, and then when A decides which offer it wants to accept, it sends another packet, which is called a request. We are requesting, A is requesting this specific IP address and subnet mask from this DHCP server. So for the request, what IP address is being used as the source? So since A doesn't yet hold this IP address, it still doesn't have an IP address, it needs to use 0000 again, and the destination is not going to be only the DHCP server that it requests, but rather broadcast. Why is that? Can you guess? Well, the answer is that other DHCP servers who might have sent offers should be aware that A has requested this specific offer and not their offer, so they don't need to allocate the address anymore. And at last, in case the DHCP server accepts the request and everything is valid, the DHCP server replies with an acknowledgement, ACK, after which A finally can start communicating with this IP address. And as I said, it's only after this packet is received, which means it cannot be sent to this IP address, so it is again sent to broadcast. All right, so this is the initial process of DHCP. When you send a DHCP offer, you include a few things here. One of them is the lease time. That is for how long I'm assigning this IP address to you. I'm not going to assign it forever. I don't want to be wasteful in case you disconnect from this network. Maybe you were using a mobile device and you're moving somewhere else. So I'm assigning you some kind of lease time, like a lease for an apartment. Before that time, there is also a renewal time where you're supposed to ask for renewal if you want to renew your subscription. If we compare that to other subscription services, or your lease time for an apartment. For that update, the process is much shorter. A already has an IP address and still has an IP address. It just needs to renew the lease. So it doesn't need to go through the entire process of discovering servers and all of that. It just says, okay, dear landlord, I know your apartment. I just want to renew my existing contract. So it sends a packet to the DHCP server called an update request. So it's asking for an update, and the DHCP server can respond with acknowledgement. This is all done via unicast now, since A already has an IP address, and this basically can say, I want the same terms of the lease that I got, but just please renew this contract by, say, 2 more weeks. This process happens way more frequently than the initial process, as it keeps on going on for a while. A short note here, for simplicity's sake, I assume the DHCP server is a standalone machine. On your network, I bet that your default gateway serves as your router, as well as your DHCP server, as well as some other functionalities we'll learn about in the future. So that's for a different video. So how will we see DHCP in action? So to do that, we actually need to either renew our lease or cancel my IP assignment and re-ask for it from scratch. So to do that, okay, so I started Wireshark in the background with a DHCP display filter. I'm going to open the command line. I'm going to write ipconfig/all at first. On Linux, you would write ifconfig/all. And this shows me the different network interfaces that I have alongside with additional information. For example, what's relevant for us now, if we look at my Ethernet network interface, we can see that it has DHCP enabled. We can see its physical address, that is its MAC address, the Ethernet address in that case. We can see the IPv4 address, and I have here an address which is obviously a private address, a non-routable address, and it says so preferred. It's preferred, which means this is what I'm going to ask from my DHCP server the next time. I also have my subnet mask here, so I know the subnet mask is of how many bits? 24. And I see that the list was obtained on March 11th, 2026, and it expires on March 11th, 2026, only a few hours later, so it's a very short list. I know what my default gateway is, both in IPv6 and IPv4, and the DHCP server, as you can see here, it's the same address, which is usually the case on home networks at least, and some additional information. Okay, let's do it side by side. So in order to release my lease, I can write ipconfig/release. And all right, I released my address for this network at least. So I released my address, and I can see I sent a DHCP packet from the source IP that I had to the destination address I knew was my DHCP server, and I sent a packet called release. So this is an option called release. I don't want to spend time going over every bit and byte here. I just want us to understand the concept of DHCP for this video. Now I can also say ipconfig renew. So I'm trying to renew my IP address, but I don't really have an IP address. So I'm going to actually ask for a new IP address. And let's see what happens here. So now I have the sequence number from the previous sniff that we had. So I'm going to remove these. They're just noisy. And look at the info here. Let's also remove the length. It's irrelevant for us. So we have the DHCP discover that I mentioned earlier. Then we have an offer, then a request, and then an ACK. And you can see this for the discover, the source was 0000, the destination was broadcast. Then the source of the offer is from the IP address of the default gateway, the DHCP server. In this case, they're the same. We're getting an offer, and it offers all kinds of things like the DHCP identifier, the IP lease time, the renewal time value, and so on. Let's see, in the discover, did I request for a specific IP address? Yes, I did. So I didn't mention it before, but once you've already received an IP address, or in general, if you like a specific IP address, you can ask for it here in advance, and you might get an offer with this IP address. So in this case, I got the IP address I was asking for in the offer. We can see it here. That's what I got as an offer. And then since I wanted this IP address, I sent a request. And again, the request is sent to the destination of broadcast in case other servers want to listen on this and release the address they have allocated for me. And then I got an ACK basically repeating the same details from the offer. And once I got this ACK, now if I look at ipconfig again, /all to see all the interfaces, I will see that I have this address assigned to me again, right here from this DHCP server with an updated timestamp. Now, if I use ipconfig renew, instead of sending the discover, offer, request, ACK, all of this process, I'm just sending a request. I'm doing it as unicast. I called it update before just to clarify that it's an update request or a renewal request, but it's still a DHCP request in terms of the option here. So it's a request that is sent from my address, that is still my address, to the destination. And then I got an ACK in this case. If the DHCP server can't or doesn't want to assign with this address, it would respond with a NACK and not acknowledge. So I know I can't use this anymore. I can't renew my lease anymore. You would also notice that all of these had the same transaction ID. All of these were part of the same process. But then when I did the next request and got an ACK, there was a different transaction ID. Okay, so we learned why DHCP is cool, why we need it, and we saw it in action, which now tells us the full story of how we learn what our IP address is. I would also say that our default gateway needs to go through the same process to get some kind of IP address from the ISP, the Internet Service Provider. But we'll talk about that on another video as well. For now, in order to make sure we understand everything, I want to ask some questions. So again, try to answer for yourselves before you listen to my answer. So yes, more questions. So what's ARP good for? ARP is used to allow a machine to find the corresponding MAC address for a known IP address, or in general, the corresponding physical address, data link layer address of a logical network address. It works by sending a broadcast request saying, hi, this is the IP I'm looking for, what is its corresponding MAC address, and then getting a unicast reply saying, hi, this is me, it could also be this is him, I know him, but usually this is me, this is my MAC address. What happens when the destination machine is in our subnet when we route an IPv4 packet? So when it's in our subnet, we assume that it's in our segment, Since it's in our segment, we assume we can get to it in one hop. That's the definition of a segment. So we're not gonna try and send it to the default gateway to route the packet outside the subnet or outside the segment, but rather we try to send it directly via one hop to the destination address. What happens otherwise if the destination machine is not on our subnet? Then we use the default gateway. We find the MAC address of the default gateway using ARP. We provide the default gateway with a packet where in the third layer, the destination address is that of the final destination. But in the Ethernet layer, or in general second layer address, the destination address is going to be that of the router of the default gateway that is then going to route this packet towards the destination. What IP header fields are related to fragmentation? So we had the identification fields, which allows us to make sure that two fragments belong to the same packet or to different packets. We have a reserve bit 0. We'll talk about that in a future video. We have the don't fragment bit, which says don't fragment if the packet length exceeds the MTU, the maximum transmission unit. Just send back an error. Don't fragment it anyway. We have the MF flag, more fragments, which indicates that this is still not the last fragment as long as this bit is on. There are going to be more fragments, and only the last fragment has this bit set to 0, indicating there are no more fragments. And then we have the fragment offset, which is 13 bits long. Since it's 3 bits shorter than the total length field, it's actually divided by 8. So we can get all of the values that we need, which also means that the length of fragments in IPv4, with the exception of the very last fragment, have a length that is divisible by 8. How is traceroute implemented? So we send the packet. By default, it's an echo request, but it doesn't have to be, with incrementing TTL. So we start with TTL of 1, then we expect the first router in the middle to reply to us saying, hey, time exceeded, you reached TTL 0, and then we learn the address of this router alongside the time it took for the packet to travel to this router and back. Then we send with TTL2, and this way we find out the next router, and so on. I would say that if you try this at home and it doesn't work, it might be that your ISP or some ISP on the way just doesn't really want to route or reply to ICMP packets because they don't seem to be as important. So they're deprioritized. It's quite frequent that it happens. Why is DHCP request sent as broadcast? So as a reminder, we have first a discover, then an offer, then a request. So I already know the address of the DHCP server I'm requesting from. Why shouldn't I just send a unicast? So the answer we mentioned here is that in case there are multiple DHCP servers, all of them need to know that I chose this specific address and this specific DHCP server. So the other ones that might have sent an offer can withdraw their offer, that is, deallocate the address they allocated for me. Alright, so we had fun. We learned many things in this video. We learned the goals of the network layer, we learned IP addressing, and there are different videos about that in depth by the whales. Include links in the description section below. We talked about special addresses, the broadcast address, this host, and loopback addresses. We also learned a bit about private addresses. We started dealing with the problem of outage of IPv4 addresses. We'll get to that in the future. We learned every bit and byte of the IPv4 header. You now know all of them. We learned about the ARP protocol, the address resolution protocol, routing a little bit. We saw a routing table. We didn't really talk about routing algorithms. That's out of scope of this specific video. We learned about fragmentation in general and specifically in IPv4, so you know how that works. We also demonstrated what it can look like. We learned about ICMP, a protocol used by our beloved IT people and people who are trying to understand the network a bit better. And lastly, we learned about DHCP, which tells us how we received our IP address in the first place, how we learn about our default gateway, our subnet mask, and some other important details for us to be functional entities within our network. Thank you so much for watching this video. I am very curious to know your thoughts about this new format of having longer videos that cover different aspects of a topic, like this one about IPv4. My plan is to publish more videos of this format pretty soon, so please do let me know your thoughts. Thank you, and I'll see you on the next video.